We're going to be moving on to velocity versus time graphs. Okay, so to start, we're going to be looking at these two graphs here. They both represent the same situation. It's a student walking to school 80 meters south from home at a constant velocity for a constant velocity of 1.33 meters per second south. Okay, so you should be familiar with the way the first one looks, the position versus time graph. Um, we see that it is sloped and it is not a changing slope. Okay, so it is a constant velocity here that we're looking at. It's not changing over time. Okay, so if we were to examine the two graphs, so the one on the right is a velocity versus time graph. It looks a little bit different, even though, like I said, both of these show the same situation. Okay, so examining the two graphs, let's talk about some of their similarities and differences. Okay, so to start, as far as their similarities, they both have the same time scale. Okay, so they both are in time of seconds, and then it jumps by increments of 15. Okay, the units are similar. Okay, so we see seconds, we see meters, same thing on this side. We have seconds, meters, seconds. Okay, so they're not exact, but they are similar. Okay, and the positive direction is the same. So south is the positive direction for this given scenario. Okay, so looking at the differences, um, the units on the vertical axis differ. Okay, so if we look, we have meters per second on the position, or just meters for position, and then meters per second on the velocity versus time graph. Okay, one of the big things is that the position time graph has a positive slope, whereas the velocity time has a zero slope. Okay, so it's just a horizontal line. There's no slope to the line at all. Okay, and then obviously the axes are labeled differently as well. So we have position, and then we have velocity for the other one. So moving on, you may recall that finding the slope on a position versus time graph in the previous lesson. So the slope of this position versus time graph was 1.33 meters per second south. So that is what we're reading on the velocity versus time graph. Okay, so we've already calculated, so the slope of this graph, if we were to find the slope, we would get the 1.33 meters per second south. And so when we look at the velocity versus time graph, this line, because it's a constant velocity, is constantly at 1.33 meters per second south. Okay, so determine the slope of the velocity time graph. So if we look at the velocity versus time graph, it is a horizontal line, and so our slope is 0. Okay, but let's look at the actual units. Okay, so for the slope, we have v2, velocity 2 minus v1 over t2 minus t1. Okay, so that would mean change in velocity over change in time. So that would be, if there was a slope, that would be the equation that we would use. Okay, and so if we break it down into units, the units for velocity are meters per second divided by second. So if we break that down, it would be meters over seconds times 1 over seconds. And when multiplied through, you should get meters per second squared. Okay, so this units, meters per second squared, should be familiar to you guys. And those are actually the units for acceleration. So therefore, the slope of any velocity versus time graph gives you acceleration. Okay, so if we were to talk about the acceleration that's occurring here, there would be no acceleration. Okay, which makes sense because they're going at a constant velocity. If the velocity was changing, then we would have acceleration occurring here. But because there's no change in velocity, it's zero acceleration. Thus, we have a zero slope on the velocity versus time graph. Okay, so for the velocity versus time graph, find the area underneath the line between the line and the time axis and examine the units. Okay, so what it's wanting is this area down here. What is the area underneath the line to the zero or to the x-axis? Okay, so we have here, it'll be to find the area because it is just a rectangle, it'll be length times width. Okay, so we have a length of 60 seconds, and then our height is going to be 1.33 meters per second south. Okay, so going back, like I said, we're doing the area is going to be length times width. So we had 60 seconds times our 1.33 meters per second south. Okay, and then when we multiply that out, you should get, okay, our seconds are going to cancel. So we should be left with 80 meters south. Okay, so we have a quantity, we have a unit, and then we have a direction. Okay, so you should recognize that this is a position. Okay, these units are telling us the position of the object. Okay, so therefore the area under the graph of a velocity versus time graph gives the displacement. All right, so we got 80 meters per second. If we look back, if we look at the position versus time graph on the left, if we look at the position at the end of the 60 seconds, they ended up at 80 meters as well. Okay, so you can kind of check to make sure that they both match. Okay, so just to sum it up, when we read the graph of a velocity versus time, it's going to give us the velocity at a particular time. Okay, if we find the slope of the velocity versus time graph, this is going to give acceleration. Okay, and then if we find the area underneath the graph, this is going to give displacement. Okay, so moving on, we have the velocity versus time graphs. Now we're going to be looking what's happening during acceleration. Okay, so you should be familiar with acceleration for position versus time graph. we notice that there is a sloped line or a quadratic line that occurs for those to show that there's acceleration on a position versus time graph. Okay, there's no um, straight lines to show constant velocity. Velocity is constantly changing. Okay, so both the position time graphs and the velocity time graphs above model the same situation. So it's a plane taking off on a runway. Earlier, we found the position of the plane by reading the position time graph and found the instantaneous velocity by finding the slope of the tangent line. Okay, so we're going to go through these different situations and use the two separate graphs and just compare how accurate the data is by reading a particular type of graph. Okay, so find the position of the plane after 5 seconds. So at 5 seconds, okay, if we're finding position, okay, go up 5 seconds, it's here. So it's a little bit past 60, not quite to 70 meters. So our position here is going to be about, I would say, like 64 meters west. Okay, and then for finding the position, remember for velocity versus time graph, we're actually going to find the area underneath the graph or underneath the line. So we're going to find the area of this triangle. So an area of a triangle equals 1/2 base times height. Okay, our base is 5. And our height in this case is 25. Okay, so we're going to find that finding the area of this, A1 equals 62.5 meters west. Okay, so looking at these two, oops, I forgot to put my bracket on this one. If we look at these two answers that we got, obviously the velocity versus time graph gave us a more accurate reading. We didn't have to guess at it. We were able to calculate it more accurately than for a position versus time graph. It was easier to just look at the position versus time graph and read it, but it wasn't as accurate as actually calculating it using the velocity versus time graph. Okay, now we're finding the instantaneous velocity at t of 7 seconds. Okay, so for the position versus time graph for 7 seconds, okay, we go up, our point is right here. And so if we draw our line, our tangent line, roughly like that, okay? We're gonna have this is our slope, okay? And so for the rise over run, for the velocity, okay, we're gonna have the ending position at like 150. So 150 meters west minus the initial was 90 meters west. Okay, divided by T2, so the final time would have been 8 seconds, minus the start time would be 6 seconds. Okay, so whenever we subtract and divide that out, we get 30 meters per second west for our instantaneous velocity at t of 7 seconds. So that was finding the slope of the tangent line. Okay, for the velocity versus time graph, it's actually pretty easy to find the velocity because the line, we just read it off of the graph. Okay, so t 7 seconds, so here's 7 seconds, we go up, so at this point, so it's actually 35 meters per second. Okay, once again, the more accurate was the velocity versus time graph. Okay, even though we calculated using the position versus time graph, it was an estimate because our tangent line, well, obviously it was not 100% correct. Okay, so the tangent line is harder to make accurate compared to just reading the velocity versus time graph. Moving on, both position and time graphs and velocity time graphs can be used to easily find position and velocity. Acceleration can easily be found from the velocity versus time graph. In this case, the velocity time graph is linear. That means that acceleration is going to be constant. Okay, so if we look back, it is linear, meaning that it's not like changing directions or anything like that. So our acceleration is constant, okay? So to find the acceleration of the plane using the velocity versus time graph, we're going to find the slope of this graph. So our acceleration is going to be v2 minus v1 all over t2 minus t1. And so if we go back and look, we're going to go from a velocity of 0 to a velocity of 40, and it took 8 seconds. Okay, so our v2 is 40 meters per second west. Our initial velocity, or v1, was 0 meters per second west. Okay, and then our time is going to be 8 seconds minus 0 seconds. So we should find that our acceleration is 5 meters per second squared west. So velocity versus time graphs can be used to create position time graphs and vice versa. We will do complete analysis of the velocity versus time graph, then use the information to create a position time graph. Okay, so here we have velocity versus time graph. So we're going to examine this and describe the motion. Okay, so if we look at this portion right here, okay, the slope is 0. So what this means is that the object is moving at a velocity of 20 meters per second east. And they're doing that for, let's see, 30 seconds. Okay. Then you'll notice that the graph changes. Okay, so we're dropping down. So we're going to go from 20, so from 20 meters per second east to 0 meters per second. So they're stopping in, let's see, they did it in 10, 20, 30 seconds. Okay, so here they're stopping, and then they're going to start accelerating in the opposite direction. So from 0 meters per second to 20 meters per second west. Okay, so that's the key. You could have put negative meters per second east, but it just makes more sense to just change the direction than to have a negative direction. Okay, so 20 meters per second west. And then it took them, let's see, it took them 1, 2, again, 30 seconds. Okay, and then they're going to move at a constant velocity of 20 meters per second west until time of 160 seconds. Okay, so that's describing the different motion there. Okay, so let me highlight. So this was that first one. This is that one. Didn't highlight this. It was pink. And blue. Okay, so that describes each part of that graph. So determining the velocity for the object after 10 seconds, and then we're going to go all the way through. So at 10 seconds here, they were at 20 meters per second east. Okay, for 20 seconds, the same, 30 seconds, the same. So I'm just going to draw a line here. Okay, that shows that those are all the same. Okay, at 40 seconds, they're at about, it's just under 15. We're going to say 14 meters per second east. Okay, and then we have at 50 seconds, it's just above the 5, so around 7 meters per second east. Okay, for 60 seconds, they've stopped, so they're at 0 meters per second. Okay, at 70 seconds, they're just past the -5, so around -7 or 7 meters per second west to show that it's in the negative direction. Okay, for 80 seconds, let's see. It's not quite to the -15, so let's say like -13 or 13 meters per second west. Okay, and then at time 90, that's whenever they hit 20 meters per second west, and they're going to continue that for the remainder of the time. Okay, one last section. So for this, what is the acceleration of the object between 0 seconds and 30 seconds? So from here to here, okay, what is the acceleration? Remember, acceleration for velocity versus time graph is the slope of the line. So the slope here is 0. So 0 meters per second squared is the acceleration because we have constant velocity. Okay, between 30 seconds and 90 seconds, which is here. So this portion, we have to do some math for this, okay? So acceleration is going to be v2 minus v1 all over t2 minus t1, okay? If we look, our final velocity is down here, and so it's -20 meters per second east. Okay, the reason why I'm not changing this to west is because I need my units to be the same in order for me to actually subtract them. Okay, for my initial velocity, it was positive 20. Okay, but we're having to subtract, so positive 20 meters per second east. Okay, and then my time, my finishing time is 90 minus 30, and we should get negative 0.6 or 0.7 um, meters per second squared east, but I'm going to change it to a positive one, so our acceleration is 0.7 meters per second squared west. Okay, if you put negative 0.7 meters per second squared east, same thing, I just switched it just so that it made a bit more sense. Okay, what is the acceleration between 90 and 160? Once again, we have a slope of 0, so our acceleration is going to be 0 meters per second squared because our acceleration is constant. Okay, so the question over here, what is the significance of 0.60, which is right here? Okay, and that's where our velocity hits 0, so the object stops and changes direction. Okay, so we're going to 0, we're basically slowing down to 0 meters per second, stopping, and then we start going in the negative direction, so going back west, so we're changing directions.